Okay, so I just wanted to introduce you to my university. So since you may not know, some of you may not know, the University of New South Wales, in short form, it's UNSW. Because we are in Sydney, we also have a campus in another capital city, Canberra, but this is the main one is in Sydney, so we call it UNSW Sydney. We were like last 2 years, we are QS World Ranking 19th and higher education ranking 84. Sometimes it varies, like last couple of years it's varying from 84 to 74 within that 10 ranking in Times higher education ranking. It's one of the largest university in Australia, so we have nearly 60,000 students because we have engineering, we have medical, medicine faculty, law, humanities, all the things. Engineering is one of the biggest, so we have nearly 10,000 students in engineering, and 2,900 academics. So in the middle of the campus, we have the electrical engineering. You can see that the electrical engineering building there is newly renovated. We are number one in Australia, electrical engineering, one of the biggest. And we have all the core electrical engineering research and teaching in our school, control, quantum engineering, microelectronics, electronics, power engineering, under power engineering, power electronics, electric drive systems, pure power system. Under microelectronics, we have just analog digital electronics, including the very like most recent one, quantum engineering. And so the New South Wales is actually the name of the state, or one of the state in Australia. It's in the east coast of Australia. Sydney is the capital, so that's why the name is on the name. The university name is on the name of the state. So UNSW. That's why University of New South Wales. Um, our campus probably is like area-wise will be smaller than probably NIT Warrangul. I think we are much more compact. A lot of buildings all close by. But we are also very close to some of the well-known tourist spots such as Bondi Beach, only 4 kilometers from our campus, 3.6 kilometers for Maroubra Beach, and so on. So if you ever visit, our university campus, you will have also opportunity to go to these places. Next, I would like to show you a few facilities that we have under the this machine, electric machines and drive and power electronics lab. So first one in your left-hand side is the wind energy system, an emulator and a generator, direct drive generator of 54 pole. The middle, you can see a electric vehicle traction drive motor and its drive system. And last one, you can see a very high speed permanent magnet motor of 100,000 RPM. All of these motors, the prototype ones, actually built by our PhD students, so it's part of PhD projects. And each one of these also have the converters, inverters, that means power electronics, and then their controls is also all our students' work. So we are strong in all three areas of a electric drive system, the power electronics, motor, and control. Now coming to the program, so I think you must have received it. It's very small, sorry about that. But the program, first day program, we will be introducing the first part, and then slowly we'll move to the electromagnetism so that we can go to the design part of the motor maybe tomorrow. So we have three sections, as you can see today, up to lunchtime today, right? 1 o'clock about. So we'll divide this. Now it is about 11 o'clock, so we have 2 hours, 2.5 hours, let's say. So we divide this 2.5 hours into 3 sections. We'll have a bit of break, 5 minutes break maybe, so that you can think what we are talking about. So we'll take a break in each sections. So first of all, I would like you to bring your attention to these figures of why we are doing transport electrification. The main reason is climate change. Probably all of you are aware of. The temperature is increasing, right? And goal is that we must keep the global temperature increase below 1.5 degrees centigrade. If we go above this, world will be in a tipping point, and there could be no return from there. Okay, so we are really in a very serious problem. That's what we should all realize. And why this temperature increase? Perhaps all of you know it's greenhouse gas, carbon dioxide. And carbon dioxide emission, one of the biggest contributors is the energy sector. And under energy sector, 73% comes from energy sector, the carbon emission. And out of that, under energy section, we have energy from industry, that's motor drives in industry. Then we have transportation, next one, which include electric vehicle in the road, boat, ship, train, aerospace, you name it. Everything actually uses a fossil fuel driven engine and contributes carbon dioxide to the environment. So one proposed solution is that we do electrify the transport so that we can reduce some of these emissions. And that's what is the motivation for electrification of transport. One very good indication of where world is moving, if we look at the investment trend. Okay, so here in this graph you can see for the last, from 2004 to 2021, how is the, where is the money moving, okay, in industry. You can see from about 2017 onward, the green one is the transport electrification, and big yellow ones is renewable energy. So up to 2017 or 2014 around, it was more renewable energy only, okay? But from 2017 onward, you can start seeing investment moving to the transport electrification as well, okay? And this means there will be a lot of money on R&D, and as well as a lot of job opportunities for the new researchers and new engineers. So we need to prepare ourselves for that, okay? And this type of courses are part of it. Now, if we look at the worldwide projected electric vehicles sale, again you can see by 2040, worldwide, 35% of all new vehicles going to be electric vehicle, okay? And what is this 35% means? It's equivalent to actually 160 billion vehicles sold, okay, new vehicles. And each of these vehicles will, if it's electrified, it will need a motor drive actually. That's what we're going to talk about, right? And 160 million compared to the cars sold worldwide, if we look at like about 400, 500 billions. So 160 billion could look like very small. But I mentioned earlier as well, this sales figure can be compared with what was in 1940, the internal combustion engine cell, okay? And in 100 years, we have now internal combustion engine driven car everywhere, right? Everything is internal combustion engine driven. So in 100 years, it will be same thing. Everything will be electrified, electric vehicle. And so that's what we need to be prepared for. And it is also driven by a lot of government policies, as mentioned previously by the director. US wants by 2026 emission to be 160 gram per mile, okay? And European Union wants 130 gram per kilometer emission, carbon emission. And India's long-term goal is to not to exceed per capita emission of developed country. Okay, so India hasn't actually set a particular goal. As far as I know, it could be different. It could change, or it might have changed in recent times. Anyone aware of anything? Does India have a goal for carbon emission, especially for car vehicle? What is that? 140? G4040, 2040 is zero carbon emission. Yeah. So 2040, 2050, right? So if zero carbon emission means we have to convert your electric cars to electric, right? There will not be any other way to achieve it, zero carbon emission. Now, you may ask why then, like why it is moving so slow, right? Why electrification of car and vehicles is slow? There are mainly two concerns. One is, of course, cost, right? We can't afford electric car at the moment. It's so expensive. And other is called range anxiety. So range anxiety is not a new thing. Actually, we also have range anxiety when we drive our petrol car, right? You are going on a long drive, and your eyes goes to your petrol. How much is there? Is there 2 point, 3 point? How much is left, right? And will you arrive at next petrol pump before running out? So this is the same anxiety you could also have for electric car. Is my battery charge will be enough to take me to my next charging point? And this is so these two are the main concern currently. What prevents the widespread take of electric car, okay? Cost and range. Now, range and cost both is contributed also by the battery. So if we look at the cost, especially cost of the powertrain of an electric car, you will see that 55% of the total cost, $55 out of $100 or 55 rupees out of 100 rupees comes from the battery, okay? And rest, 45% comes from the motor, power electronics converter, and controller, okay? So this course, we are not going to talk about battery at all. So we will be concentrating only on that 45%, okay? Because there's a lot of research already on battery and other sources. So we will not talk about battery, but the other 45%, what can be done, okay? And so in the first section, our learning goals, I have make 3 goals for us. So you will be able to describe what is a powertrain, electric powertrain, and then we will be able to classify electric vehicle, and that you will also be able to list desirable performance of electric motor and EV traction drive. And all these goals will be ultimately linked to how the cost and the range we can improve on. Okay? So that will be our first section's goal. And then second section will have some other goals and so on. So let's move to first. Let's look at actually the classification first, okay? Let me just make this one a little bit bigger. I go like this. Okay. So we can divide electric vehicles broadly into three categories: hybrid electric vehicle, plug-in hybrid electric vehicle, and all-electric vehicle. Okay, so hybrid electric vehicle, I believe, already been advertised in Indian market by various companies, right? So it's more or less looks like similar to what you are driving. It's only the powertrain inside is a bit different. You will have a battery, usually a smaller battery, and you still have your engine, you still need your petrol. But the petrol engine could be used to drive the motor, or which will behave like a generator actually. You can produce electricity there and use that electricity to charge the battery. So everything happens inside, so you may not even aware of it. That if happens, that engine is used to drive the car as well as run a generator to charge battery, and the generator also contributes to drive the car together. We call it hybrid electric vehicle. Okay, you don't have to charge the battery outside, you don't have to plug in, and this is the easiest option. So it's already quite popular, several cars quite popular, even in Indian market it is coming. Then the other one is plug-in hybrid vehicle. So in this case, internal structure is still same, but you could have a plug-in point. So you can charge the battery outside as well. Okay, not just the generator producing electricity and charging the battery, but also you can externally charge the battery. And then the all electric car, most popular, well known, is the Tesla. Perhaps some of you have seen, heard, or even been advertised in India. Of course, very high end, very expensive, but that's the electric car which has become the standard kind of Tesla. And in this, you don't have engine, you don't have combustion engine, you don't have any, you don't need any petrol. It is simply battery, a motor. You could have more than one motor, but motor and battery only. So we call it all electric. And this battery you must charge through outside supply. So plug-in, it's a plug-in all electric vehicle. Okay, so we can categorize like this. But in all three cases, the motor, power electronics, control is pretty much same. So whether you do it for hybrid or for or electric, it's same. Only power ratings will be different. High voltage will be different. Voltage level will be different. But basics will be very, very similar. Now let's look at how this power train in the components, the key components, and how it relates. Okay, so most of you drive cars, so you are those who drive car at least familiar with, right? Once you press your accelerator, engine accelerates. So in electric vehicles, the same thing. You press your accelerator pedal, it becomes actually a command. Okay, it could be a speed command or it could be a torque command for a controller. Output of the controllers is going to be a PWM signal for the inverter. Okay, and the inverter is supplied through the battery. So one side is DC and the other side will be your three-phase AC, and that three-phase AC supplies the motor, three-phase motor. And the motor drives your car or drives your wheels. Now, the battery, it could be up to 800 volt. Proposed DC bus is currently 600 volt, but they are talking about bringing it even to high level 800 volt. So why high voltage such as 800 volt? You can charge the battery quicker with high voltage. Okay, so one of the other problem is charging, right? Petrol pump, you go to your petrol pump, you want to fill the tank, it takes how many minutes? 5 minutes? 5 to 10 minutes. But if you want to charge the battery, you need at least, with the fastest charger, 20 minutes. Okay? So, like that's a problem, right? So that therefore, it's a big research area how to improve this charging. What can we do? Okay? And also, there is the other, some solutions there, especially for two-wheeler, three-wheelers, the technology calls battery swapping. Maybe, I don't know whether it has come to India or not, but battery swapping is that the battery is like a plug-in, plug-out type of thing. So you can take out the battery, put another battery there, fully charged battery. So that will take you a few minutes, which is quite convenient. And it's a big technology. Battery swapping technology is big in China, I understand. Okay, they were even trying to do it in passenger car, even large vehicle like trucks. Okay, for those type of vehicle, charging is a really, really big issue. How quickly you can charge, right? So battery swapping seems to be a good solution there. But the car like Tesla, we can't do it because battery it's under the floor of the car. So you cannot take all the batteries out of it and then put new ones. It's just impossible. Okay. So if we want to do battery swapping technology, the architecture of the electric car need to be completely different. Okay. So this is the area where India could look at actually, like completely designing their own technology rather than taking what Tesla has proposed, right? That's what China is doing. They try to make their own things. They have made the electric car cheaper. The latest car from China is BYD. It is like they're making it at least 10-15% or up to 20% cheaper than Tesla. So if they can do it, why not us, right? Why not India? Right? That's what we need to think about. To think differently, out of the square. So that battery, anyway, it could be up to 800 volt, and then you could have a DC-DC converter to reduce it down for the lower voltage that you require for your auxiliary power supply. And you could have a onboard charger. So this picture shows you the key components and how they are linked to the system. So this is what like easily understandable with this picture. At least I find it very easy to understand how electric car works, basically. And I talk about cost. So now let's look at that 45% of the cost, which comes from power electronics and the motors. So this pie chart actually dividing that 45% to, again, under various components. So we have an inverter, we have a DC-DC converter, then we have transmission lines, cables, connections, and a motor. So you may note that the motors and power electronics inverter are actually 60% of the cost. Okay, so if we can reduce cost there, there will be it can like influence the total cost. And so to make it widespread, the electric vehicle, we want it to be cost effective, and cost reduction can happen in motor and power electronics as well as with the battery. But as I said, this course will be only concentrating on motors and power electronics. So for us, there, the cost effectiveness. And we can increase the range by making the motor and power electronics, the whole system, drive system, one, of course, efficient, more efficient, and second, making it lighter and smaller. So how the lighter and smaller can help us? If your powertrain is lighter and smaller, the whole vehicle's weight and size could be smaller. So if it is smaller size and weight, you have better aerodynamics. When the car moves, there is air drag, right? The motor has to overcome that air drag. Now, a lighter and compact car, you can have a better aerodynamics. So that can help you to increase your range, actually. So efficiency and power density both together can contribute to improve the range, okay? And making the system smaller and compact also help us to reduce cost, because smaller size, smaller, that means less requirement of critical minerals such as copper, rare earth, magnet material, etc. So that also influences the cost. So usually this becomes the design goals for when you design the drive systems for electric vehicle, these three: efficiency, then power density, and cost. This is actually from the US Department of Energy. They have published a set of specification for electric car. It's called Freedom Car 2020 specifications. And according to that, you can see the power is not that high. It's only 30 kilowatt, and maximum peak power is 55 kilowatt. Speed, there are two speeds, you can say rated speed and maximum speed. So we'll talk about it, what this speed means. So rated speed is only 2,800, and maximum could be up to 14,000 RPM. Then if you, other components or other parameters, although important, but what I would like you to see is this: the volume and mass. Okay, so volume, they want the volume to be less than 9.7 liter with less than 35 kg. So this relates to our power density. And the speed here, this 2,800 to 40,000, the speed ratio here, you can see, this is known as constant power speed range, or CPSR. So we'll talk about why this is important for EV and why you would like your motor to have wider CPSR when you design for electric car. And of course, we talk about the efficiency. Okay, so these specifications tells us what are the requirements we should have for future electric car. And you may note this torque versus speed characteristic here. So this part, you can note that torque is constant and then torque falls. So when torque falls, this is the basic P is equal to torque times speed from physics, right? Most of you know. So if torque falls when speed increasing, what does it mean? Power can remain constant. Okay? So here, if we draw the power characteristic, so power will increase when torque is constant and speed is increasing. And when torque falls, speed increasing, power will become constant. Okay? So that's why this speed ratio is called constant power speed range. Okay, but we'll talk about why it is important a little bit later. Up to here, let's think what are our key points so far. Or do you have any questions up to here? Yes. 18 seconds. So that is the your acceleration time, it could be, okay? But you can see it is, you need the peak power and peak torque only for very small or short time. So it is, this peak torque and peak power is intermittent rating. It's not continuous rating. You do not need 55 kilowatt for continuously. You only need 55 kilowatt only for 18 seconds, okay, to accelerate, okay? During acceleration, you need the highest power. So you get that, if you get it in 18 seconds, so your power only need to, your motor only need to provide 55 kilowatt only for 18 seconds. So you can put large amount of current without burning the motor, and it is only for 18 seconds, right? So that's the significance of 18 seconds. So how did they come up with 18 seconds? I am not sure, okay? It is, they must have done some kind of research, and 18 seconds found to be the most optimum for acceleration. Probably it gives the drivers a comfort. If you accelerate too fast, that is also sometimes not comfortable for some drivers, right? Only for those who are doing a racing car, for them, they want the thrill to accelerate as quick as possible. But for our drivers like us, we want to accelerate comfortably. So 18 seconds may be coming from that sort of things, okay? Any other questions? Yep. So 325 is the, they are talking about the rated voltage battery, DC bus battery, DC bus of the, your motor scene will see 325 rated and 450 volt. So you could have your line to line voltage equal to 415 volt for the motor. Okay, because when you do the inverter with a 2-level 3-phase inverter. Yes, sorry, where is that? This is the one you are talking about, right? So battery voltage could be higher, okay, because you could have a DC-DC boost converter as well, or you could, buck converter. You can reduce it, the voltage seen by the motor, you can reduce it. But you could, battery voltage could be higher, like up to 800 volt they are proposing. So why 800 volt? As I mentioned, it could help you to do the charging fast, because you can. I don't exactly know how much it was allowed, but I believe if you talk about a ripple, right? Fluctuation is basically ripple in your DC bus voltage. So it's not more than 5 to 10%. You should not allow more than 5 to 10% in the DC bus fluctuation. Yes. So that for what motor sees, okay, this specification is actually for a motor design purpose, okay. This 2020 Freedom Car specification, when they provided, they wanted the traction motor to achieve all this, okay. For that purpose, the motor should see at least that range, okay. Not too low, not lower than 200, or not higher than 450, so within that range. But battery voltage could be higher, okay. And there is a reason why you want to keep the voltage low for permanent magnet motor, is that if your controller fails and motor is speeding, it will have induced voltage, uncontrolled induced voltage. So if that voltage is higher than what battery can withstand, then it can burn the whole system, okay? So that's why you want the motor voltage to be relatively lower. You don't want a motor with 800 volt, okay? Because if you have 800 volt and you can't control it, then it's spinning at a very high speed, it can exceed 800 volt and it can burn the system, okay? Anything else? So let's think about the key points so far together. What's the key point so far? Sorry? Types of EVs. Okay. Good. Let's try to recall, right? Otherwise, we sit here and after some time we'll forget what we have talked about. So let's try to write it down. Okay, types of EV we have talked about. Anything else? Key components of EV, right? EV traction drive. Cost and range, right? Cost and range challenges. Yes. So remember this when we move to the next part, right? Okay, so let's move to the next one. So next part, we'll be talking about the fundamentals of the traction. So let's, like before, let's try to think of what are the key points so far. This time I can't write because I'm using a different laptop, so you have to write your own key points. Okay. CPSR, okay? Importance of CPSR and CPSR, okay? High power? High power density, yes. Kilowatt per kg and kilowatt per liter, right? Anything else we remember? Loss minimization, yep. Copper and core loss minimization. Types of motors, right? We look at 3 motors basically which are used for traction motor. Anything else we remember? Comparison of all the motors, okay? All right? Okay, so we talk about the motors, we talk about CPSR, we look at power density of these motors, and we are actually all these things are pointing you toward PMSM, right? But just remember that PMSM may not be always your solution, okay? Sometimes for some applications, some other motors could also be good, but you may have to compromise somewhere, like you may have to compromise on efficiency or power density, but you may want to have a cheaper motor. So in that case, maybe motor without permanent magnet is good. Okay, so always remember that it depends on application as well and your requirement. Next part actually we would like to talk about is how to calculate the power for a traction motor, okay? And we will start with, in fact, the very basic equation. This equation probably some of you are familiar, or most of you are familiar, right? This is called torque balance equation. So your left-hand side, Tm, is the motor torque. J is the inertia and the acceleration. So that component is sometimes known as acceleration torque. After that, you have D is the friction or viscous friction coefficient times the speed. This torque is sometimes referred as damping torque as well. Or the last one is the load torque, TL. And this equation is like common for any motor-driven system, okay? Usually the inertia, the total inertia could include the motor inertia as well as your load inertia together, okay? And if you have gear between your motor and the load, which is in our traction drive system, we will definitely have a gear, a reducer usually. You can see there in the picture here. Let me just get the, can I get the, sorry, this is your one, so I'm not sure, the laser pointer. Maybe here or here. This one maybe. The laser pointer. Yeah, that one. Okay, so that's good. Thank you. So you could have the gear, as you can see in this bottom picture. So you could have a viscous coupling, that is your d omega m. That will, the viscous friction is represented by this torque, 3 omega m. And then you have the gears, okay, a reducer or reduced gear systems, speed reducers, basically. So if you have gear, then we could refer the load torque to the motor side. So this is how do we refer them? Usually you multiply your this friction coefficient d or your inertia j by square of the gear ratio. Okay, this referring from one side to other side comes from the same concept as your transformer. You may remember you can refer secondary to primary, primary to secondary. So it is somewhat similar. You can refer from motor side to load side. And its concept is also same. When you refer from primary to secondary side, you multiply it by square of the turns ratio, right? So here we multiply it by the square of the speed ratios, okay, which is the gear ratio. So we can write the same torque equation also if we have gear, referring everything to the motor side. And when we do that, we will multiply the motor and load torque by the square of the gear ratio and the damping or coefficient also by square of the gear ratio, and load torque we multiply it by the gear ratio, okay, not square. Remember that torque is not multiplied by square, it is only the gear ratio. So same equation can also be used for geared system after referring the quantities. And in this we will be interested to calculate actually this Tm, that motor torque, as well as the power related to it in a electric traction system. And the load torque, TL, is your actually tractive force demanded by the wheel. Okay, so if we know TL, and we can estimate inertia and also damping coefficient roughly, so we will be able to calculate out the motor, the torque demanded from the motor and power demanded from the motor. So this is what we will try to do, okay, in the next slides. Now, what are the forces that the motor has to overcome? First of all, you have to overcome the gravitational force, right? That is mass. So let's consider the worst case. When a car moves on a slope, it requires the highest amount of force, right? So let's say the road has a slope of an angle beta. So then the force, the gravitational force is mass times gravitational constant g times sine of that slope angle, sine beta, is the force, gravitational force need to be overcome by the motor, first force. The second one is the force on the friction force of the wheel. When the wheel moves on the road, it has to overcome the friction of the wheel tire on the road. So that force is also in fact related to your gravitational force, but it's cosine component, okay? mg cos beta. So this force, this rolling, is sometimes referred as rolling resistance force. This force is in fact is always present whether you have the slope or not. Okay, if your slope angle is 0, this becomes mg. If you have slope angle 0, then in fact this gravitational force mg sine beta becomes 0. Okay, so if you have slope, that this you have an additional force mg sine beta. If you don't have a slope in your road, then this force, gravitational force, becomes 0. Sine component becomes 0. But cosine component is always present, and usually it's multiplied by how rough your road is, okay, by a coefficient known as rolling friction coefficient. And this coefficient is empirically determined, so you can find out what is this value for a rough surface or for pitch road or for concrete road or whatever. Okay, so this value will be different, usually less than 1, 0.4 to 0.35 to 0.4, about that. You can find, actually, if you look for it, possibly even for Indian roads, you may find this information, what is the rolling coefficient for Indian pitch road. For, I think, US or even for some Australia, it's like 0.35 something. So for India, it will be similar, maybe slightly different, but you can find that value, okay? And then third one is the aerodynamic drag. When the car moves, car has to overcome the air force from the air, right? Air friction, basically. Okay, so this, which is known as aerodynamic drag force, and it's calculated from the density of the air, half time density of the air, multiplied by the cross-sectional area of the front of your wheel, AF, times the square of the velocity, times a coefficient or constant known as aerodynamic drag coefficient, CD. And this CD is, again, could be different for different vehicle, because it depends on the design of the vehicle, actually. For example, here at the bottom you can see there is a kind of like Jeep type of vehicle where the front area is much larger. So this coefficient CD is about 0.5, whereas for a passenger car where your front area is relatively smaller or narrower, it is 0.3. Okay, and so it could be different for different type of vehicles. And so this force, this aerodynamic force, we should also remember that this, if we multiply this force by velocity, we get the power, right? So power related to aerodynamic force or aerodynamic drag force is, if we multiply this force by velocity, the power becomes actually function of cube of the velocity. Okay, so higher the speed of your car, higher will be this dragging force. Okay, and you can calculate out for the worst case scenario, the highest speed, what will be this force. Okay, so we can calculate all these three forces, and together, if we sum it up, we will actually get the your total force, which is actually your load related to load torque or load force. Okay, that in our previous slide, the TL. So TL relate to this force, actually. If we multiply the force by radius of the wheel, it will become torque. Okay, and the if we ignore the damping coefficient, usually D is very, very small in our previous torque equation, D times omega. So if we assume there is very little viscous friction, D is very small. So if we ignore D omega m term, then in terms of force instead of torque, the difference between the motor's tractive force force required from the motor minus all this force that we have to overcome is equal to your acceleration force. Okay? If the car is not accelerating but just running it steady state, then this accelerative term becomes 0. Okay, at steady state this is 0. So at steady state, tractive force is equal to the force required by the tractive force of the motor equal to the force that it need to overcome, which is the rolling resistance, air drag, and the gravitational force if there is a slope. Okay, so we can calculate out from there what is the force required from the motor, and if we multiply the force by the radius of the wheel, we'll get the torque. Okay, so very easily it can be calculated, and usually when we express it in the terms of force and linear velocity, this mass is multiplied by a factor higher than 1, known as sometimes called the rotational inertia coefficient. This in fact just account for mass of the motor or the mass that is present in the additional mass that is present in the car, like passengers, let's say, or weight or something. Okay, so this factor increases the total mass of the car body. And this equation, that when we convert this to torque by multiplying by the radius, which is the wheel radius, we will immediately know what is the torque required by the motor. And this equation we can compare kind of a very basic equation of let's say the pulley system. Okay, in pulley system, remember a motor is in the has the rotational motion, and a mass moves linearly, right, going up and down. Car, it is actually same thing. The motor rotates, but the car moves linearly, right? It's not going up and down, but it's going horizontally, moving at a certain velocity. So using that concept of this pulley drive system, we can calculate out also the equivalent inertia of the rotating mass in the motor system. Okay, you can compare these two equations here, and this linear mass moving up is equivalent to a equivalent inertia, the mass time r squared. Okay, similarly here, so that means the total inertia is not just the inertia of the motor, but this m times r squared. So that means the inertia is slightly higher. So that's the factor which is accounted by this km in our equation. Okay, this is the equivalent linear mass, equivalent inertia when you convert it. So we could calculate torque, and we can also calculate power directly from there. So this is the starting point. Actually, if you are doing a traction design, this will be your starting point. Okay, calculate the torque and power from this basic equation, and then from there onward you do rest of the things. Okay. This is an example. I think we'll share the slides later, right? So you can look at this slide. This is a numerical problem, a very simple numerical problem, which shows how you can calculate this power for a car moving with a slope. Okay, how these forces are calculated numerically using those equations just we talk about. Okay, I can give you a few minutes to have a look because it's just maths. I don't need to read out. You can look for yourself. Okay. this is a small car. As you can see, it only needs 20, sorry, how much kilowatt? 29 kilowatt, okay? It's relatively small motor using a 42-volt battery, so it's kind of a small system, okay? But you can use the same process to calculate the power of any other car, okay? We have taken the break, we have, so we'll move forward. So this is the last part of today's, I think. We'll take maybe 20 minutes. Will be okay, right? Okay, we'll try to do this in 20-30 minutes. So rest part is actually refresher on electromagnetic, as we said. We can probably move quite fast because this is most of you should be familiar with. It's more about recalling certain things so that we are ready tomorrow's actual design problems. Okay, so that's why we will be doing this part. In case someone hasn't done electromagnetism before, this will help them as well. So this next